A mixed inhibitor is actually quite common. This is one that binds to an allosteric site like it did in non-competitive inhibition. But remember, in non-competitive inhibition, the inhibitor could bind to either the free enzyme or the enzyme substrate complex with equal affinity. But a mixed inhibitor binds with greater affinity to one or the other. In other words, it prefers the free enzyme or it prefers the enzyme substrate complex. And so this is actually more common. It turns out that non-competitive inhibition, purely non-competitive inhibition, isn't really very common, but mixed inhibition certainly is. The scheme for this I'm not going to draw out because it's basically the same as it was for non-competitive. It's just that the values Ki and Ki prime end up not being equal because it's the inhibitor is going to bind with greater affinity to one of those forms of the enzyme. And we'll skip the Michaelis-Menten plot for this one. It's a little bit uninformative. The Lineweaver-Burke plot's a little more useful to look at. But just recognize the inhibitor's binding in an allosteric site, so that part is not competitive, right? Binding within the same place that the substrate is, but that there is some influence, right? That's what we're saying by this, that the binding of substrate influences the ability of the inhibitor to bind and vice versa. And that by definition has a competitive aspect to it. It does not mean that the active site is still binding the allosteric site. It's just that there's some communication from that allosteric site to that the substrate. And that's why we call it mixed, because it has both a competitive and a not competitive aspect to it. Just like before with non-competitive, the effective enzyme total has been lowered. There's always going to be some fraction of the enzyme population that's bound to that inhibitor, and therefore Vmax apparent will always decrease, will always be lower than Vmax. But now Km gets confusing because Km, the way it changes depends on if the inhibitor binds better to the free enzyme or the enzyme substrate complex. And so that makes things a little more complicated for this. So I want to look at the Lineweaver-Burke plot for mixed inhibition. This is 1 over initial velocity, again 1 over substrate concentration. And for same thing as usual, we've got 3 different inhibitor concentrations. So the first one with the shallowest slope will be inhibitor equals 0. And I will draw a line connecting those like this. And then we'll add some inhibitor. So inhibitor equals 1. And this will be interesting. And then finally we'll add some more inhibitor. This is inhibitor equals 2. And the key thing here is that these will intersect. You'll notice that the y and x intercepts are all different. So Km apparent and Vmax apparent are going to be different from those values. The Vmax apparent will always be lower, as we said, but the Km apparent, it kind of depends on whether it's going to bind better to the free enzyme or the enzyme substrate complex. And then the last form of reversible inhibition we're going to talk about is uncompetitive inhibition. This one's a little different because we're actually, most cases of uncompetitive inhibition occur when we have a second substrate involved. And so that would look something like this. So the free enzyme, and I'm not going to use S this time because we actually have more than one substrate. You're familiar with using A and B as 2 different substrates. So the enzyme and A come together to form the enzyme A complex. And under normal circumstances, right, this would combine with the second substrate to form the EAB complex, just like we talked about before with, say, a sequential mechanism. But what can happen here is this EA complex can combine with that inhibitor to form the EAI complex. And so what that might look like is in a normal reaction, maybe like before we saw we have a deeper active site where, say, A binds within here and maybe B binds on top, and then there's a reaction that occurs. An uncompetitive inhibition, we would see that, just like normal, A would bind here, but then the inhibitor would bind sort of in the binding place where B would bind, and of course we're not going to get a reaction as a result of that. Let's look at the Michaelis-Menten plot for uncompetitive inhibition, typically we'll have initial velocity as a function of substrate concentration, and we will see our normal rectangular hyperbola. For the normal reaction, no inhibitor. We'll have our Vmax value, and of course our Km value here. And now if we add the inhibitor to this, we actually see something kind of unusual. It might look a little unusual in that this gets pretty steep, but then it very quickly does that. And so now its Vmax is like here, so that's the Vmax apparent for the plot where we've added some inhibitor. And what you'll notice is that the Km apparent is less than Km. That's interesting. So why is that? First of all, the effective enzyme concentration has been lowered, as we've seen, because adding more substrate, or A, won't flush out the inhibitor. So if we look back at this situation here, a competitive inhibitor, normally we'd be able to add substrate and we would then diminish the effect of the inhibitor, but adding more A is not going to have that effect. In fact, adding more A is going to make more of the enzyme A complex and give more of the species that the inhibitor can bind to. So it's definitely no competitive aspect to this. And so what that means is there's always going to be some population at any concentration of A where the inhibitor is bound and the complex is ineffective. So we will see a decrease in Vmax. In other words, Vmax apparent is less than Vmax. Now what's interesting is the formation of that inhibitor complex shifts the equilibrium toward the formation of EA. So how do we interpret that? So think of Le Chatelier's principle. If I have added inhibitor, I'm actually pulling this equilibrium this way, right? I'm pulling and forming more enzyme A complex. Well, that's kind of similar to saying that you've increased the affinity without actually doing it, increasing the ability of E and A to bind. And so that shifting of the equilibrium in that direction, we see it in the data as it looking as if the Km apparent has decreased, that we've actually made EA bind more tightly. It's not actually true. The enzyme and that A substrate bind with the same affinity. It's just that that equilibrium is pulling it forward and gives the appearance of a reduced Km value. So the Lineweaver-Burke plot for this one looks kind of interesting compared to the other ones we've been looking at. We will still do the same thing, 3 different inhibitor concentrations, but this time if our inhibitor equals 0 plot, of course, looks like this. What we see with this, though, is the lines, this line will be parallel to the previous one, and same with this one, the increased inhibitor. These lines are parallel, so they never actually intersect. And so that, again, should make sense in light of what we were saying up here. Let me continue these lines down. Here we have the intersection points for the uninhibited reaction, right? Vmax is a certain value, but then as we add inhibitor, that Vmax value decreases, the reciprocal value increases. And as we think about Km, here Km is a certain value. The reciprocal is small, so the actual value is large. And when we add inhibitor, now the reciprocal value is larger, right, this whole distance, and thus the actual real value is smaller. So this Lineweaver-Burke plot of uncompetitive inhibition, just like we've seen before, this certainly does illustrate the trends of the Km and Vmax apparent that we've been looking. And quickly, just looking at the equation for this stuff, again, we have this Ki prime, we have this alpha prime value modifying that, just like we saw with the mixed inhibitor. Because it's combining with the enzyme substrate complex, we give it the prime. And we can see the values of Km apparent would decrease because we're dividing by that alpha value, which is always going to be greater than 1. And similarly, the Vmax apparent will also decrease because we are dividing by that alpha value. Types that we've talked about. I'm not going to go through this step by step, but this line by line, but this is a good reference.